for those of you who joined. So we're very happy to have Matias von Bell from the University of Kentucky. So Matias is a graduate student working with Martha Yip. And today he's going to talk about a unifying framework for the nu-Tamari lattice and principal order ideals in Young's lattice. So take care.
Thank you very much, Alejandro, for that introduction. And as you said, my name is Matias von Bell, and this is joint work that I'm presenting today with Rafael González D'León, Francisco Mayorga Cetina, and my advisor, Martha Yip. And so I'll be talking about a unifying framework for the nu-Tamari lattice and principal order ideals in Young's lattice. So perhaps I should say that, give a little preface of what's coming up. So the unifying framework here is going to be that these two lattice structures appear as dual graphs in a triangulation of a certain polytope. And so that's where we're headed. But I'll start by telling you what this Greek letter nu here means. So the choice of nu here is so that I can say that I've proven lots of new results. No, but just kidding. In all seriousness, the nu here represents a lattice path that looks like this. So you take any lattice path from the origin and end it at some point BA, in this case 5, 3. And so that's a new path, and a new dict path is any path that's weakly above that. And so we're going to get a lattice structure on these new dict paths, that we saw during pre-seminar, the nu-Tamari lattice. However, we're going to define the nu-Tamari lattice in a slightly different way, this time using ij trees and forests instead. So we take a partition of n and of the set 1 through n, and such that 1 is in I and n is in j. So it's a disjoint union of I and j. So we have a nice example here for n equals 10. And we construct a we construct a bipartite graph here from this set as follows. So the bipartite graph is it's Kij, the size of I and the size of j, and we add arcs to it to form what's called an ij forest. And the arcs have to satisfy two different conditions. So the first one is that the arcs are increasing, so they go from an element of I as the left endpoint to an element of j with its right endpoint. And the second condition is that the arcs are non-crossing, so that they aren't crossing when we draw them in this way. So I could not add this arc here, for example, because that would introduce a crossing. And also I can't add this arc here because that's not increasing. All right, so this is an ij forest. And when the arcs are maximal, so that I can't add any more arcs, like in this case, without violating one of these conditions, that's an ij tree. All right. And I want to point out while we're here that we can now define what's called the nu-Tamari complex. So it's going to be a simplicial complex of ij forests that are determined by nu. So as a simplicial complex, you can also think of it as the minimal non-faces of the complex are pairs of crossing arcs. And you might have seen the letter nu here show up now and wonder how this relates to ij trees and forests, because there doesn't seem to be a lattice path immediately here anywhere. Instead, the lattice path shows up here as a sequence of north and east steps. If we make a correspondence here between elements of I and north steps, elements of I and east steps and elements of j and north steps. And specifically, we take all of the letters here except for the first one and the last one. Those are just there to guarantee that this original definition here, condition on the top, is satisfied. So that 1 is in I and n is in j. All right, so these are ij trees and forests. So
so the sequence of that's the sequence of nu.
Yes, this sequence here in the big box is nu, as long as we ignore the east and north at the beginning and end. And so one thing that's true is that the sequence here, the lattice path, determines a set ij, and vice versa. So if I have a set ij, then that determines a lattice path, and a lattice path determines the set ij. Yeah, good question. So then also on these ij trees, we can define this operation called an increasing flip. So we flip one arc to an increasing arc. So if we look at the left end point of these arcs, it's going to be a bigger value on the right. So left end point is a 5 here, and it's a 1 here. And you can flip an arc if you can do this operation and end up at an ij tree again, so that there's no crossings occurring. And with this operation, we can then define a cover relation similar to the one that we saw previously in the pre-seminar, where one object is covered by another if we can obtain it by, in this case, an increasing flip, whereas in the pre-seminar, it was a rotation of lattice paths. And then this allows us to give another definition of the nu-Tamari lattice, and this was given by Ceballos, Padrol, and Sarmiento. And this is the ij-Tamari lattice, and it's a lattice in ij trees given by the transitive closure of this operation.
Matias,
Let's look at, yeah, go ahead.
question, do you need to have that k is smaller than j bar, or would you be allowed to just like completely translate later?
So we can't have, that's not going to be possible because these are maximal trees, so there would be something obstructing it.
Okay, thank you.
Yeah, so it always has to look like this because these are maximal trees. But yeah, that's a good question.
Sorry, maybe you're going to show it there, but are you going to show how to get the lattice path from the non-crossing tree?
I wasn't actually planning on telling you that and just stating it here.
Okay, perfect.
We can talk about it afterwards. I'm happy to share. I have a slide actually to show that, but in the interest of time, I thought I would omit that. So sorry to cheat you a little bit here. But here's the Ceballos, Padrol, and Sarmiento's version using ij trees and the corresponding Préville-Ratelle and Viennot version on the right. But there is a correspondence between objects here that's fairly natural, but takes a second to explain. So I decided to omit it. But yeah, so this gives another characterization of the nu-Tamari lattice. And we talked about flow polytopes at the pre-seminar, so I perhaps will just quickly mention this again. So taking a flow graph with vertices n, and then I have, we add edges ordered from smaller vertices to larger vertices, and then we define a flow of size 1 to be a tuple of non-negative real numbers, so that flow is preserved at every vertex here. So we have one flow coming in, one flow exiting, and then flow is preserved in the intermediate vertices. And when we consider the flow, when we consider the set of all possible flows of size 1 on this graph G, we obtain the flow polytope. So flow polytopes are what we will be triangulating today. So we need a method to triangulate them. Oh, and I guess one more thing I should say is that the vertices of a flow polytope are routes. So here, if I take a maximal path from the source all the way to the sink, and if all my flow goes through here, that's going to give me a integral point in Rn with the appropriate, or sorry, Rm with the number of edges being m. And so this is going to correspond to a vertex in my polytope. So I might use vertices and routes interchangeably today. But to triangulate a flow polytope, there's a particular way to triangulate them called a framed triangulation. And we obtain that by first introducing the notion of a framing on a vertex I. And so a framing at a vertex I in the graph is a linear order on the incoming edges and a linear ordering on the outgoing edges. So in this case, we just order them from top to bottom in this planar embedding. And a framed graph is in a graph where all of the vertices will have this sort of pair of linear orders on the incoming and outgoing edges. And we don't need to define it for the source and sink, I suppose. And then this framing we can use that to define a notion of coherence of two routes. So if my route P is in red here, and my route Q is in blue below, then two routes are coherent if PI and QI, which are the portions of the routes that lead up to I and end at I. So if I cut it here, I end up with PI on the left and IP on the right. So I want to order these PI and QI and IP and IQ and make sure that they're ordered in the same way. So what I mean by that is at this vertex I, we travel backwards until the paths diverge. So at this point is where they diverge. So they differ, these two paths. So now there's an ordering here. There's a framing on these incoming edges here. And that framing will determine the order of PI and QI. So in this case, PI is on top and QI is on the bottom. So I will say that QI is less than PI. And we do a similar thing in the other direction, just symmetrically. And now we get that IQ is less than IP. And then what we do is compare these two with each other. Okay, Q is less than the P counterpart in both of these cases. So then we can say that these are coherent at a vertex I. And with this coherence relation, we can, at a vertex I, we can then say that two paths are coherent if they're coherent at every common vertex. And then we can collect these coherent routes, mutually coherent routes, into what's called a clique. And this will now allow us to define a framed triangulation of a flow polytope. And that was given by Danilov, Karzanov, and Koshevoy in 2012. And it goes as follows. So if I have a graph with a framing on it, then let delta C denote the convex hull of vertices of the flow polytope corresponding to routes in a clique C. Then if I take the set of all of these convex hulls of vertices corresponding to maximal cliques in the graph, then that gives me a top dimensional, well, every one of them gives me a top dimensional simplex, and the collection of all of them gives me a triangulation, and that triangulation is regular and unimodular. So unimodular here, that guarantees that we can count the volume by counting the number of simplices. So just a quick example of this one so that we're on the same page. If this is my graph, I end up having 5 different routes in the graph. So I have, I can break that down into 2 maximal cliques. Here's the first one on the left, and there's another one on the right. And you can notice that they're all the same except for this pair differs. And that's because these two pairs, or this pair is, these two edges, sorry, these two routes are incoherent. You could see that they would cross each other if we put them both in here under this framing that's induced by this embedding from top to bottom. So then now we can kind of gain insight on the structure of this flow polytope over this graph. So it's the union of 2 simplices. And so we can imagine what that would look like, even though it's ambient space is what of dimension, it's a 5-dimensional. Well, it lives in 5 dimensions, but it's a 3-dimensional polytope. Okay. So now let's talk about what the actual flow polytope that we are going to be discussing today is. And that's going to be called the nu-caracol flow polytope, and it's built off of this nu-caracol graph. So nu here is our lattice path. We take a lattice path, and we then begin by starting with the path graph with the number of vertices being the y-coordinate of this endpoint of the path nu, +3. So the path graph on A + 3 vertices. Is there a question in the chat? Yeah, caracol is snail in Spanish, and so you'll see soon why it's called that as I build this. So here we add then these edges below here, all excluding the first edge to the sink. And then after that, we add edges on top based on the number of E steps. So here we end up with this graph. I'll show you how the E steps influence it here. So there are 2 e-steps in the first run of e-steps here. So we get that nu1 is 2. And so we add 2 edges right here from 1 to 3. And then there's a single e-step. So that gives us the single edge here from 1 to 4. And then there are no e-steps starting at this base of this north step. So we don't have anything here to 5. And then we have 3 and then 1. And so we end up with 3 edges here and 1 here. So a lattice path nu now determines this kind of a graph. And it looks really pretty, like a snail shell, hence the name. And so the flow polytope over this flow graph is the nu-caracol flow polytope. And an integral equivalent version to this was studied by Mészáros and Morales, and they found that its volume is given by this determinantal formula here. And this actually counts the number of nu-dic paths as well. So this is the determinantal formula for the number of nu-dic paths that I mentioned briefly in the pre-seminar. Okay, and so this flow polytope is what we're going to be triangulating. And so we wanted to think about the dual structures of those triangulations. And so that's what motivated our study. So the first thing that we proved was that the dual graph of the planar frame triangulation of this nu-caracol flow polytope is the Hasse diagram of a principal order ideal generated by nu and Young's lattice. So I should tell you what the planar framing is real quick here. So at a vertex 4, if I have this planar embedding of this graph nu, then I labeled the vertices from top to bottom in increasing order. And so that gives me a framing that's induced by this planar drawing. And I make sure to draw this so that the horizontal path is, say, on the x-axis, for example. And then with this framing, we obtain the dual structure of the triangulation to be the principal order ideal in Young's lattice generated by the corresponding Young diagram that corresponds with the lattice path nu. And so here's ignoring the rest of Young's lattice, this is what we obtain. And there's a nice correspondence between these lattice paths and then actually the lattice points in the lattice paths with the routes in the nu-caracol graph. And I won't go into the details of the proof for this one, but I would just like to point out that the proof relies crucially on a result by Mészáros, Morales, and Jessica Stryker. So Carola Mészáros, Alejandro Morales, and Jessica Stryker, they showed that in a planar framing, the routes being coherent is the same thing as the routes being non-crossing. And so that was essentially what was needed to produce this. But then the next framing that we looked at was the length framing. And that one gave us the dual structure of the Hasse diagram of a nu-Tamari lattice. And so the length frame is also a very natural framing on the nu-caracol graph. So if we look at 4 again here, just ordering these by length. So the longest one is on top, 1, 2, and then 3. And the outgoing edges, the longest one is on top. And the length, we can think of it as the difference between the endpoints of an edge. And when there are multiple edges, it really doesn't actually matter which one you label how. But anyway, with this framing, we obtain a triangulation whose dual structure is the nu-Tamari lattice. So the proof of this, I did want to kind of give you an idea of what this looks like. So the sketch is as follows. We define a bijection from all the routes in this nu-caracol graph to the set of possible arcs in the set ij. And the bijection is given by this following labeling of the edges leaving the source and the edges coming into the sink. So if we label these by e steps going upward here from the edges leaving the source and the incoming edges to the sink, we label them with north steps it going down. Then the routes in the nu-caracol graph have this property that they're fully determined by their initial and terminal edge. So we can read a arc simply from looking at the corresponding edges, terminal and initial edge that was used by that arc. So that particular route there corresponds to an arc from E1 to N2, like this. So that bijection then can then be extended. Well, you of course have to show that it's a bijection, well-defined and so on, but once that's done, it extends to a bijection from maximal cliques to these IJ trees. And to make sure that happens, you have to show that the coherence of these routes in the nu-caracol graph is the same condition under the translation as the non-crossing of these arcs. So here's a nice big picture of an entire simplex under this extended bijection being taken to the corresponding IJ tree. All right, and so with this bijection, then it becomes pretty easy to show the dual structure, because the combinatorics of a simplex is really fully captured here in this in the IJ tree with all the arcs corresponding to the vertices. And so two simplices in a triangulation are adjacent if they differ by a single vertex or a route in our case. And so the corresponding IJ trees then have to differ by a single arc. And the only way those do that is by the rotation, or sorry, increasing flip that we talked about before. So then that gives us the dual structure that we want. And we know that that structure has the structure of a lattice, so the result follows from there. Okay, so some corollaries that I wanted to mention how this, some results that follow from this is that this gives the geometric realization of the nu-Tamari lattice and as the dual graph of the length frame triangulation of our flow polytope. But this isn't the first such realization. There's been plenty others by Ceballos, Padrol, and Sarmiento who initially studied it. And the three that they gave were, one was the one skeleton of a polyhedral complex induced by this arrangement of tropical hyperplanes that they called the nu-isosahedron. And another one is the dual of a regular triangulation of the subpolytope, Uij of a product of simplices. And then the last one was as a dual of a coherent fine mixed subdivision of a generalized permutahedron. But don't ask me about this one. I'm not as familiar with this one. But our length frame triangulation turns out to be integrally equivalent to this subpolytope here, the triangulation of this subpolytope that they considered. And so another consequence of this bijection that we have between routes and arcs is that the length frame triangulation is really the simplicial complex. If we think of the triangulation as a simplicial complex, it is really just the nu-Tamari complex. But something interesting that I find is that a consequence is that now Mészáros subdivision algebra can be used to triangulate this subpolytope of the product of simplices. And this follows from Mészáros' work on triangulating flow polytopes with the subdivision algebra. And now that we have a description of this polytope, subpolytope U as a flow polytope, we can triangulate that as well. And this was something that Ceballos, Padrol, and Sarmiento wondered about in their study. And so we can now answer that in the affirmative. It's still being typed up at the moment, but coming out soon. Okay. And then just various quick connections to some other things that have been studied that I should mention. So in the classical case, when nu is the staircase path, perhaps better there, then the classical Tamari lattice and the positive filters in type A root poset, which is has the same structure as the principal order ideal generated by the classical staircase nu. these have appeared together as dual graphs before, but of subdivisions of the Pitman and Stanley polytope. And so our work serves to generalize these structures and then also unify them under the same umbrella of DKK triangulations of a polytope. So when these two structures originally appeared as subdivisions of the Pitman and Stanley polytope, they were obtained using different methods. So now we can obtain both of them under one type of triangulation technique. Then another thing to point out is that for the planar graph, since the nu-caracol graph is a planar graph, Mészáros and Morales and Stryker's results extend these dual structures into certain triangulations of certain order polytopes as well. And then finally, I also wanted to point out that the H vector of the nu-Tamari complex is given by nu-Narayana numbers. This was shown by Ceballos, Padrol, and Sarmiento as well. And so then that gives us that the H star polynomial of our nu-caracol flow polytope is the nu-Narayana polynomial. And we obtained another proof of this as well using a Schelling order on the triangulation induced by the planar framing. So there are two proofs of this fact. But some further questions that I wanted to end with is that I still have what graphs appear as dual graphs with other framings. We picked two very natural ones. Could have picked, any variety of framings and different graphs might pop out. So in particular, are any of these lattice structures on nu-Catalan numbers or on nu-Catalan objects? Are any of them hiding in the mix? And then also, can this work be extended to type B? So I'm currently working on this. I think there are some methods that we can apply from Ceballos, Padrol, and Sarmiento's study of the type B Tamari lattice that might now help us think of flow polytopes in type B. That's something I'm currently thinking about. So these are my questions. Now I'll turn it over to your questions. So thank you.
So let's thank Matias. We could put in the chat or your reactions. Are there any questions for Matias?
I have a little question. So is it possible that if you define your new dict paths to be all the paths that stay above a certain path, and then you can similarly define horizontal distance and then maybe get similar results or sort of an analog version of your results?
So I'm not maybe entirely sure what analogs you mean, because I think so the dual structure that we obtained it using the IJ tree description, but there is a natural conversion between the IJ tree and the rotation on the nu-dict paths. So they give the same structure. So I'm not sure if I understand it exactly what you mean, but I think the answer is that they give the same structure. I don't know if that answers your question.
Yeah, I was just wondering why you were focusing on the path that is above a given.
Oh, yeah.
And why not just below that?
Oh, above and below. So that's the distinction you were making. Yeah. So I think it would be, you could define all of this as below as well, and you would obtain, I think, similar results maybe. I would have to think a little more about that. But I think it would require a different definition of the nu-caracol flow polytope.
And there's no restriction on nu, right?
Correct.
Nu can be any path.
Yeah.
It doesn't have to be above the diagonal or anything.
Right, that's right. Well, there's a tiny detail that I maybe should mention is that we assumed throughout this entire talk that nu starts with a north step. I didn't really clarify that, but that's actually a condition that isn't really a big deal. We can, geometrically, things are essentially equivalent in terms of volume. If we don't really need any restriction on the path nu, as long as it's in the positive quadrant.
Let's thank Matias again, so still here, and thank you, Matias, for the great talk. And I'll stop the recording, so we'll make another noise.
Thank you very much.